Friends, family, YouTubers, lend me your ears and your eyes. Now take a look at this and tell me if you like what you see. Now just what exactly is going on here? To find out, just keep watching. If you're like most people, you probably had a really terrible or series of really terrible maths teachers growing up. People who just didn't have a love for mathematics or were poor at communicating. The result, an entire portion of the population who are cut off from a source of beauty that would enrich their lives. Now, if you don't think this is a problem, then I sympathise, but please try to imagine something, say music, literature, or cinema, that deeply enriches your life with its beauty or its insight, and now imagine not being able to appreciate it. It's kind of sad, isn't it? That's the way I feel about mathematics. So if you're one of those people who has never said that's beautiful about something in mathematics, I'm going to try and change that today. I'm going to show you something that will make you think differently about prime numbers forever. Now I want you to think back to your childhood. How were prime numbers explained to you? Well, I don't know about you, but I was always told that they are numbers which are only divisible by 1 and themselves, and by no other numbers. Okay, fair enough. This is strictly true. But does it give you a sense of what they really are? Or do they remain an abstract mathematical concept, shrouded in mystery? Well, at least for me, it's the latter. As time went on, I grew more and more familiar with the prime numbers. I learned all sorts of interesting facts about them. That they are the building blocks of all numbers, that there's an infinite number of them, and so on. However, it wasn't until a few years ago, in 2012, that a software engineer named Brent Yorgi came up with the concept of factorization diagrams. And this is what I'm going to show you today. But first, let me start with a real-world example that I think illustrates prime numbers extraordinarily well. Let's say you're with a group of friends and you have a collection of delicious morsels that you want to share evenly. As my example, I've chosen the humble Tim Tam, a delicious chocolate-coated biscuit that's as Australian as Vegemite. Now let's start with a non-prime number of these. Let's say 6. And let's just say it's you and one other friend. Can you share them evenly with your friend? Why certainly, each of you will get 3. It's not rocket surgery. What about if there's 3 of you? Yep, no problem. Each of you gets 2. And that exhausts all the way you can evenly share 6 things. And now onto a very serious matter. Do any of you actually know how many Tim Tams are in a packet? Anyone? Anyone? It's 11. And it's a prime number. And dun dun dun! Arnott's Biscuits, the manufacturers of Tim Tams, almost certainly do this on purpose. For 11 biscuits cannot be evenly shared amongst any number of people. Nope, can't be done. Oh my God, Sean, you say. How can this be? Please tell me it's not true. My world is imploding. Yes, prime numbers have the awe-inspiring property that they cannot be split, or should I say, divided, into evenly sized groups. Now, how would you represent this visually? Let's have a look at 6 again. You can arrange 6 either this way or this way. In fact, I'd say this. If you can arrange a number of objects in a rectangular pattern like this, it's not prime. Or to put it another way, if you can't arrange the objects in a rectangular pattern, no matter how hard you try, then it is prime. It's as simple as that. That's pretty bloody interesting, if you ask me. Now, let's get on to Brent Yorgi's factorization diagrams. I can't be 100% sure, but I think he had an ulterior motive with his diagrams. He wanted you to be able to see that prime numbers were actually the multiplicative building blocks of all other numbers. So let's ask ourselves a question. If we've got a prime number, and we know that it can't be evenly grouped, then how would we represent it visually? Yorgi's solution, which works really well, is to evenly space the objects around a circle. So for instance, 7 will look like this, and 11 will look like this, and 3 will look like this, and 2, a little counterintuitively, will look like this. But Brent Yorgi also had the genius idea of making his diagrams recursive. How should we represent 6? Well, what we can do is find the largest prime factor, 3. Okay, now what do we do with it? I guess that means we need to place 3 identical diagrams around a circle. But what is the diagram? Well, we can just recursively apply our process. The next and final factor is 2. So we just place the diagram for 2 evenly around the circle in 3 places. And this is what we get. And we can continue this process as many levels as we want. Take the number 30, which is 2 times 3 times 5. We end up with this diagram. It's 5 diagrams of 3 diagrams of 2, the final prime factor. We have recursively applied the method 3 levels deep. This is what we mean when we say that primes are the multiplicative building blocks of numbers. Each number has a unique decomposition into prime numbers, and these diagrams show that very nicely. So, now it's time for me to show you another little software project of mine. While going for a jog one day, I suddenly had a flash of inspiration. What if I created a counter that instead of using Arabic numerals, used factor diagrams instead? What would this look like? Would it look cool? The answer was far more gratifying than I could have hoped for. It just looks awesome. Let's have a look. Let's start at 1 and count up. There's 2, 3, 4, 5, a circle, 6, 7, another prime in a circle, 8, 9 looks really nice, 11, prime, another circle, 13, a circle, 17 will be a circle, as will 19. Another prime. "27 is beautiful. The next one like that is 81. We're coming up to a square number soon, 36. I think you'll find it's quite beautiful. Look at that recursive structure. Now let's speed up the animation a little, and I'll just let you soak it in for a while. If you'd like to play with this effect a little bit more, please go to seanseafreak.org/effects/factor diagrams. I've put the URL at the bottom, and have a play around. Alright, thanks for watching. I'll see you again with some other random thing I find interesting soon. Until then, see you later.